All right, we have a topic to cover that's actually not in your textbook, okay? So I'm going to call this section 310, but if you look for 310 in your textbook, it's not there, okay? But this is an important required topic for us to cover, so I'm just going to give you some examples, and if you have questions, of course, let me know. And the topic is polynomial and rational inequalities. So we've been talking about graphing polynomials and rational functions, and how do we find asymptotes and zeros and intercepts, all of those things. But now we're going to talk about inequalities. All right, so here are the steps that you use if you have a polynomial to solve a polynomial inequality. So first we have to express it. We have to get 0 on one side. Okay, we move everything else to one side, so we have 0 on one side of the equation of the inequality. Then we're going to solve an equation to find boundary points. Okay, the boundary points are going to happen when f of x equals 0, which means at the x-intercepts, or the roots of the polynomial, which we've been doing a lot of, right? We've practiced finding zeros or roots of polynomials. So we're going to find those zeros or roots, and those are going to be our boundary points. We use those boundary points to divide the number line into intervals. We choose a test value in each interval to see if the original equation inequality is true, and then we write the solution set. So let's do a few examples. And we're going to come over here. So the first example that we'll do is, what if we have this inequality x squared, make it so you can see, x squared minus 7x plus 10 is less than or equal to 0. Okay, where is that going to be true? Well, let's just think about what's even going on here. This is a parabola, and it's going to open up, and we're wondering where it's less than or equal to 0, right? So I don't know exactly what this parabola looks like yet. It could look like this and not be less than 0 anywhere. Or it could, it could just touch the x-axis, right, and be less equal to 0 at that one point. Or it could be less than 0 on this whole interval, right? We don't know what the case is, but those are our three options: nowhere, at one point, or on an interval. All right, let's see what we can do. So that's step one, is to make sure we have this on one side and 0 on the other of our inequality. And now we're just going to solve an equation. Let's set it equal to 0. So quadratic equal to 0. We are pros at this. We can factor or use a quadratic equation. We can factor this one, right? This is going to be x minus 5, x minus 2. So the intercepts happen at x equals 5, x equals 2. Those are our boundary points. Okay. So now we just look at a number line, and here we have 2, and here we have 5. And now our number line has 3 intervals. And I'm going to choose a number in each interval. I'm going to choose 0 and put it back into my original equation and see if it, or inequality, and see if it makes it true. So 0 is easy. If I put in 0 for x, I get 10, which is not less than or equal to 0. Nope. How about something in here like 3? 9 minus 21 is minus something. 9 plus 10 is 19, minus 21 is negative 2. Negative 2 is less than or equal to 0. So yep, this interval works. How about 6? Maybe I should write things down. 36 minus 42 plus 10. Let's see, 46 minus 42 is 4, which is greater than 0. Nope, that doesn't work. All right, so it looks like this is the case that we have, right? The parabola dips below the x-axis, and between 2 and 5, this is the case. So our last step is to write our interval. This is true on the interval from 2. Let me just write 2 greater than or x greater than or equal to 2 and less than or equal to 5, right? And we use these inequalities because our original inequality was less than or equal to. At those boundary points, it would be equal to 0. Okay. All right, let's try another one. What if we have 2x squared plus x greater than 15? Okay, well, the first thing we need to do is make sure, get 0 on one side. So we'll bring x squared, or sorry, we'll bring 15 to the other side of the inequality. And now we will write an equation. Okay. Can I factor this? Let's see. I'm looking for things that multiply to negative 30 and add to 1. Yeah, I could break this into plus 6x minus 5x minus 15. And then use grouping, and I'll get x plus 3 minus 5x plus 3. And I'll factor out an x plus 3, and I get 2x minus 5 equals 0. Hopefully that looks familiar to you. If that doesn't look familiar to you, you might need to go back and do that factoring practice, the optional factoring practice, okay, because to just remember how to do grouping or factor something like this. All right, so what are my boundary points? X equals negative 3 and x equals 5 halves. All right, those are going to be my boundary points. So just notice again, we have a parabola, right? All right, so my number line is going to look like here's negative 3, here's 5 halves. With something easy in here, I'll choose 0, right? 0 is always an easy one to choose. I put it back into my original inequality and see if it makes it true. 0 plus 0 is greater than 15. No, it is not. How about negative 4? 2 times negative 4 squared minus 4. So this is going to be 32 minus 4. Is that greater than 15? Sure is. How about 3? Right, 3 will be over here somewhere. So 2 times 3 squared plus 3 is going to be 18 plus 3. Is that greater than 15? Sure is. Okay, so these two intervals are where this original inequality is true. So I will write my solution as negative infinity to negative 3, and then I'm going to not include that because of original inequality was just greater than, and union with 5 halves to positive infinity. And let's just think, just for practice, let's graph this, right? This is a parabola. It opens up. Where's the vertex? The vertex is at minus b over 2a, so at minus 1/4. So at minus 1/4, we have our, we can put our x-intercepts at negative 3 and 5 halves. And this is going to open up, right? So at negative 1/4, somewhere around here, the parabola is going to look something like that. I guess I could say the y-intercept is at negative 15, so I probably should have made that a lot lower. So this is not a very impressive graph of this parabola, but we can see where is it greater than 0? It's greater than 0 here, and it's greater than 0 here, right? Those are our intervals, okay? Okay, let's do one last example of this. There was the top of the paper. X cubed plus 3x squared minus x minus 3 is less than or equal to 0. All right, so this is a cubic, not a quadratic. How can I factor this? How can I solve for my boundary points? Well, we could use some of the tools that we had before. We could find the possible rational zeros and try dividing them to try to get this to a quadratic. That would work. I could also just try to factor this because I notice these first two terms have a common factor, right? Oh, let's set this equal to 0 and start factoring. X plus 3, I can factor that out, and I get x squared minus 1 equals 0. And now I have a difference of squares, so I have x minus 1, x plus 1 equals to 0. Great. So what's my number line look like? At x equals -3, -1, and 1. So now I have actually 1, 2, 3, 4 intervals that I need to test a number on, right? So I'll put them back into my original equation. So -4 cubed plus 3 times -4 squared minus -4 minus 3. Right, I just chose a number over here in this interval. -4 squared is -64. This is going to be 16 times 3, which is 48, plus 4 minus 3. I don't know. This is 52 minus something bigger than that. This is going to be less than or equal to 0. So yeah, that interval is going to work, right? How about if I choose -2, something in this interval? -2 cubed plus 3 times -2 squared minus -2 minus 3. So I get -8 plus 12 plus 2 minus 3. So 14 minus 11 is 3, which is greater than 0. So that interval does not work. Ooh, nice. I can choose 0 in this interval. So that's just going to be -3, which is less than or equal to 0. So yep, that works. And now how about 2? 2 cubed plus 3 times 2 squared minus 2 minus 3. So 8 plus 12 minus 2 minus 5 is going to be greater than 0. So this interval does not work, right? So my intervals, my solution is going to be -infinity to -3, and I'll include a square bracket because my original inequality had less than or equals to, union with -1 to 1 with square brackets. Okay, on those two intervals, this original inequality is true. So those are polynomial inequalities.